Imagine for a moment, maybe you've just been denied a loan you really needed, or uh, perhaps a complicated medical diagnosis has just been given to you. Or maybe, and this one's pretty unsettling, you're riding in a self-driving car and it suddenly makes a really unexpected move. How does that feel? When those critical decisions, the ones that really impact your life, your health, your safety, when they're made by AI and you have absolutely no idea why, it's unsettling, isn't it? And that feeling, that lack of clarity, it comes from what we call the black box problem in artificial intelligence. AI models have become incredibly powerful, no doubt about it. They make decisions affecting us all the time, but how they actually work inside, often it's a complete mystery.
Exactly. And explainable AI or XAI, it's much more than just a technical puzzle for engineers. It really represents a fundamental shift almost in how we build these systems, how we use them, and maybe most importantly, how we interact with them. Because they are so deeply woven into our lives now. At its heart, XAI is about transparency, it's about interpretability, and ultimately it's about building genuine trustworthiness into these algorithms that, well, they govern so much now.
That's a really important goal. And to get there, we first need to sort of peel back the layers on this black box idea itself. So today, that's what we're doing, a deep dive into this fascinating and honestly critical field of explainable AI. It really is about prying open that black box, not just for tech reasons, but for, ethical reasons, legal ones, societal ones too. In this deep dive, we're going to unpack what this black box problem really is, why it's become such a huge imperative across so many industries. We'll look at how experts are actually building systems to try and explain the unexplainable. And we'll explore where the future of understandable AI might be heading everywhere from healthcare to finance to, yes, those self-driving cars. Let's get started. Okay, so the rise of AI, it's been incredibly fast, almost dizzying, right? We see it in core functions everywhere, complex medical diagnostics, navigating high-speed financial markets. And it's all been fueled by this unprecedented predictive power. These systems can handle vast amounts of data.
At speeds we just can't match.
Exactly, finding patterns, correlations we never spot. And this is the crucial point we're digging into today. This power often comes with a big cost. Opacity. The systems making these vital decisions become unclear. And that brings us right to this black box problem. So when we say black box in AI, what exactly are we talking about? Basically, it's a system where you see the inputs, right? You put data in, and you see the outputs, the prediction, the decision.
Inputs are clear.
But the middle part,
Yeah.
the intricate logic, all the calculations, the specific pathways that turn input A into output B that remains hidden, opaque. This is especially true for the really advanced stuff, like deep learning models.
Right, those huge neural networks with millions, sometimes billions of parameters.
And also the big language models, the LLMs like ChatGPT that everyone's talking about now. The paradox here is pretty striking, isn't it? The very complexity that makes them so powerful is also what makes their reasoning so obscure, even for the people who built them sometimes.
That's a key point. And this opacity, it doesn't always come from the same source. It's really crucial to understand that difference because it shapes how we approach XAI solutions. We can broadly break down the origins into two main types. First, there's what you could call intentional obscurity. This is like a black box by design.
Okay, so someone chooses to hide it.
Exactly. Developers or companies deliberately conceal the model's inner workings, maybe the algorithms or the source code itself. It's not an accident of complexity, it's a strategic decision. Usually it's about protecting intellectual property.
Like a trade secret.
Precisely. The model's architecture, how it was trained, the specific weights that could be a huge competitive advantage they want to guard. So they might patent things, use code obfuscation, or just offer it via an API where you only see inputs and outputs. It's a business or legal strategy.
Okay, that makes sense. What's the other type?
The second origin is organic complexity. This is where the system becomes a black box almost naturally as a result of its own learning process. Think about those deep neural networks, again, hundreds of layers, billions of parameters, all adjusted during training on massive data sets.
Right.
Even the creators who understand the high-level design find it practically impossible to trace exactly how a specific decision is made. It's not like following simple if-then rules. The knowledge is distributed across all those connections in a really complex, nonlinear way.
So it's not hidden on purpose. It's just too complex to follow.
Exactly. It's a fundamental scientific and engineering challenge. The scale and the way it learns just surpasses our ability to directly inspect every step. The model learns powerful, but ultimately inscrutable ways of representing the data.
That distinction is really important, and it leads us straight into this central dilemma, doesn't it? This trade-off between how well a model performs and how easy it is to understand.
Mm.
Often the best performing models, the most accurate ones, they're also the most opaque, the most like those black boxes.
That's a very common pattern, yes.
And you can see why in high-stakes areas, finance, medicine, security organizations might accept that mystery. They want the best results, the most accurate diagnosis, the best fraud detection.
Mm-hmm. Even if they don't fully grasp the why behind it, the performance benefit seems worth the opacity.
But, and this is where it gets really interesting, that trade-off, accepting the mystery, it hides some significant risks, real-world dangers. For instance, a model could be getting the right answer consistently, making us feel confident,
Right.
but doing it for completely the wrong reasons.
Yeah.
Spurious correlations, maybe.
Exactly. That's the classic clever Hans effect you hear about sometimes.
Oh, the horse that could supposedly do math.
That's the one. Turned out Hans wasn't calculating. He was just reacting to tiny unconscious cues from his trainer. Got the right answer, but the reasoning was totally flawed.
And this happens with AI, too.
Oh, absolutely. There's a really compelling example with an AI built to predict pneumonia risk. It learned a very strange pattern. Patients with asthma seem to have a lower risk of dying from pneumonia.
That sounds wrong. Asthma is usually a risk factor.
Precisely. It doesn't make biological sense. What the AI missed was the context. Asthmatic patients, being high risk, were actually getting much more immediate aggressive care when admitted. That's what lowered their mortality rate.
Ah, I see. The AI just saw the correlation in asthma, lower death rate, without understanding the cause.
Exactly. It learned a dangerous, misleading pattern. Without explainability, that flawed logic could have stayed hidden, potentially leading to terrible outcomes if doctors relied on it.
Wow. And it's not just flawed logic, is it? Opacity can hide other things, too.
Definitely. It can mask security vulnerabilities, making systems susceptible to attacks. It can lead to data privacy violations, maybe revealing sensitive information inadvertently. And critically, it can hide and even amplify systemic biases that were present in the training data.
Like in hiring or loan applications.
Yes. If an AI learns from biased historical data, it might learn to discriminate based on race or gender, even if those aren't explicit inputs, maybe using proxies like zip codes. That perpetuates harmful stereotypes. And this brings us right back to why distinguishing between intentional obscurity and organic complexity is so vital for XAI. For those intentionally obscured proprietary models, XAI mainly plays an external role auditing, ensuring compliance.
So checking if it's fair, if it follows the rules, without needing to see the secret recipe.
Exactly. Regulators or auditors need to verify fairness, lack of bias, legal compliance. They don't need the source code for that. And post-hoc explanation methods, the ones applied after the model is built, are perfect for this. They analyze behavior from the outside.
Okay. And for the organically complex ones.
Their XAI serves a much more fundamental purpose, often for the creators themselves. It's about discovery, debugging, safety engineering. Data scientists need it to understand what the model actually learned, why it fails sometimes, how to make it safer and more reliable.
So it might even lead them to build different kinds of models.
Potentially, yes. For really critical applications, understanding the limits might push them towards building intrinsically interpretable models right from the start, where transparency is designed in. So, you see, XAI isn't one single thing. It's a whole suite of tools, tailored for different kinds of opacity and different needs for understanding. It's about choosing the right approach for the specific black box you're dealing with. And in response to all these challenges from opaque AI, the field of explainable AI has really emerged and grown rapidly. Formally, you could define XAI as a collection of processes, methods, and techniques designed to render the decisions and outputs of AI systems transparent and comprehensible to human users.
Making sense of the black box, basically.
That's the core objective, to demystify it by providing clear, meaningful insights into the model's logic. What features does it focus on? What patterns does it see? How important is each piece of information? It's not just technical. It's about responsible AI aligning technology with human values and societal needs.
And the goals of XAI, they're really multifaceted, aren't they? Covering technical, ethical, legal, social aspects. What's fascinating is how interconnected they seem. Like a virtuous cycle, almost. The first big one is just fostering trust and confidence. That feels fundamental.
It is. People are just more likely to trust and use AI if they understand why it's doing what it's doing, especially in areas like healthcare or finance where the stakes are so high.
Right. It moves it from being a mysterious oracle to something more like a reliable partner.
Exactly.
Then there's ensuring accountability and responsibility. Transparency is key here, right?
Absolutely. By showing the decision path, what features were used, how they were weighed, XAI provides that crucial audit trail. That makes it possible to find errors, spot bias, understand harms, and figure out who or what is responsible when things go wrong, which is essential for fixing things.
And that leads into the third point, enabling auditability and compliance, with regulations growing.
Organizations have to prove their AI is operating legally and ethically. XAI provides the evidence needed for regulators, helping comply with things like the EU's GDPR, which even includes a right to explanation. It's about proving responsible operation.
Fourth, and this seems incredibly important, is promoting fairness and mitigating bias.
Yes, this is a huge function. XAI acts like a diagnostic tool. By revealing what features the model relies on, you can see if it's using sensitive attributes like race or gender, maybe indirectly through proxies.
Like using zip codes as a stand-in for race, perhaps.
Precisely. XAI helps detect that, allowing developers to correct biases and ensure the AI promotes equality, not disparity.
Fifth, for the people building these systems, XAI is vital for improving and debugging models.
Immensely valuable, yes. It helps data scientists confirm a model works as intended, and crucially, that it's not just relying on some random correlation in the training data. Identifying weaknesses helps refine the model, improve data quality, and build more robust systems overall.
And finally, the sixth goal, empowering users and enabling contestability. This is about giving power back to the individual.
Exactly. It's about human agency. Someone denied a loan or rejected for a job by an AI, an explanation helps them understand why. That gives them a basis to challenge the decision, or even give them actionable insights on what they could change to get a better outcome next time.
It moves beyond just computer says no.
Right. It becomes computer says no because of X, Y, and Z, much more helpful. And you're right, these goals aren't separate. They really feed into each other. That foundational goal of transparency, achieved through XAI methods, enables everything else. Transparency allows auditing for fairness. Auditability establishes accountability. A system proven fair and accountable earns trust. Trust encourages wider adoption, which then increases the demand for even more accountability, driving the need for better transparency tools.
So it really is a cycle.
It is. The key takeaway is that XAI isn't just optional. It's the essential linchpin connecting the technical side with the ethical and social legitimacy needed for responsible AI.
That connection between transparency, trust, and accountability is really clear.
Yeah.
Okay, so we've spent a good amount of time on why XAI is so important. Now, let's shift gears a bit and get into the how. What are the actual tools, the techniques that experts use to crack open these black boxes and get those explanations?
Right, the XAI toolkit. It's quite diverse, as you might imagine, reflecting the complexity of the problem. But we can categorize the methods to get a better handle on them. Understanding these categories helps navigate the trade-offs we talked about, especially between performance and interpretability. The most fundamental split is between intrinsic interpretability and post-hoc explainability.
Okay, intrinsic first. That sounds like it's built in.
Exactly. Intrinsic interpretability, sometimes called white box modeling, uses models that are transparent by design. Their internal logic is accessible. You can follow the path from input to output without needing extra tools. Explainability is part of the architecture.
Like building with glass instead of concrete.
That's a great analogy. You build it to be seen through from the start. Then you have post-hoc explainability. These are techniques applied after a complex black box model is already trained. They don't try to take the black box apart that might be impossible or the code might be proprietary. Instead, they approximate its behavior or explain individual predictions by observing its inputs and outputs.
So they work from the outside, trying to figure out what's going on inside.
Pretty much. And they're essential because we have so many powerful opaque models already in use that weren't designed for transparency. Post-hoc methods bridge that gap. Beyond that main split, we can categorize further. There are model-specific versus model-agnostic methods.
Okay, what's the difference there?
Model-specific methods are designed for a particular type of algorithm, like SHAP is optimized just for tree-based models, taking advantage of their structure. Model-agnostic methods, on the other hand, are designed to work with any machine learning model, regardless of how it's built.
So more versatile.
Much more versatile. That's why methods like LIME and the general version of SHAP are so widely used. They can tackle almost anything. And one more distinction. Local versus global scope. This is about how broad the explanation is. A local explanation zooms in on a single prediction. Why this decision for this specific input? Great for debugging one error or explaining one result to a user. A global explanation tries to describe the model's overall behavior. How does it generally make decisions? What features matter most overall?
And can methods do both?
Some can. SAP is particularly noted for providing both local and global insights, which is incredibly powerful for understanding a model at different levels.
Let's dive into those intrinsic models first. The white boxes. It seems like the ideal, right? A model that's just clear from the start.
It often is the ideal, yes, where transparency is paramount.
Like decision trees, you mentioned them earlier. They seem very intuitive.
They are. Think of a flowchart. Each step is a test on a feature. Is income $50? Yes or no branches lead to the next test, or finally to a decision leaf loan approved.
And the explainability.
It's inherent. You can easily trace any path and read it as a clear if-then rule. Makes them great for regulated industries where you must justify decisions. Plus, features higher up the tree are generally more important.
But you mentioned a limitation. Accuracy.
Right. A single deep tree can overfit the data. And to get better accuracy, people use ensemble methods like random forests, hundreds or thousands of trees combined.
And then it becomes a black box again.
Exactly. The ensemble is powerful, but you lose that simple transparency. You can't easily track all those paths.
Okay, what other white box models are common?
Linear models are another classic example. Things like linear regression or logistic regression. Their math is usually straightforward, often a weighted sum of the input features.
Like price, weight size,
Yeah.
plus weight bedrooms, that kind of thing.
Precisely. And that weight, or coefficient, for each feature directly tells you its impact. Positive weight means more of that feature increases the outcome. Negative means it decreases it. Very clear.
So the logic is right there in the numbers.
Yes. And then there are rule-based systems. These are often built from expert knowledge. Explicit if-then rules like, if patient has fever and cough, then test for flu. The logic is totally transparent, defined by humans or clear inference.
Sounds very explainable. The downside.
Usually simplicity comes at the cost of predictive power on complex, messy, real-world data where relationships aren't so neat and linear. That's where black boxes often outperform them. And that reality needing the performance of black boxes is why post-hoc techniques are so critical. They let us use powerful models and still get some explanation. They analyze input-output behavior without needing access to the internal code. And two of the biggest names here are LIME and SHAP.
Okay, let's start with LIME. What's the core idea there?
LIME stands for Local Interpretable Model Agnostic Explanations. The key word is local. It explains one prediction at a time. The clever idea is to approximate the complex black box's behavior just in the immediate neighborhood of the specific prediction you care about using a much simpler interpretable model.
So it builds a mini model just for that one explanation.
Essentially, yes. It works like this. First, perturbation. It takes your specific data point and creates lots of slightly different versions by tweaking its features a bit. Second, prediction. It feeds all these slightly altered versions into the original black box to see what it predicts for each one. Third, fitting a surrogate model. It then trains a simple model like linear regression or a shallow decision tree on this local set of perturbed data points and their predictions. That simple model is the explanation for the original point.
That sounds intuitive, and it works for any model.
That's a major strength. It's model agnostic. Works for tabular data, text, images. It's also generally faster for single explanations than SHAP.
What are the downsides?
Well, it's purely local, so no global insights about the whole model, and sometimes the explanations can be a bit unstable. Slightly different perturbations might give slightly different explanations, which can be confusing.
Okay, so LIME for local, quick insights. What about SHAP? You mentioned it's theoretically stronger.
Yes, Shapley additive explanations has really gained traction because it's grounded in cooperative game theory, specifically Shapley values.
Game theory, how does that apply?
It treats the prediction as a game and the input features as players collaborating to reach the outcome. SAP calculates the fair contribution, the Shapley value, for each feature player. It figures out each feature's average marginal contribution across all possible combinations of other features. It's a very rigorous way to assign credit.
And that gives it certain guarantees.
Yes, a key property is additivity. The sum of all the SHAP values for a prediction perfectly equals the difference between that prediction and the model's average prediction. It ensures the explanation is complete and consistent.
That sounds powerful. What are its main strengths?
The biggest is providing both local and global explanations. You can see why one prediction happened, like LIME, but often more robustly. And you can aggregate these values to understand the model's overall behavior, like which features are most important globally.
Yeah.
It's also model agnostic and has great visualizations.
The catch. Is it slow?
It can be, yes. Calculating contributions across all feature combinations is computationally very expensive, especially with many features. That's the main drawback. Also, the standard approach might sometimes struggle a bit with highly correlated features, potentially misattributing some impact if not handled carefully.
So, choosing between LIME and SHAP, it's not just technical, it's strategic. Depends on what you need the explanation for.
Absolutely. It's a trade-off. Speed versus rigor, local versus global scope.
If I'm a data scientist just quickly checking a weird result, maybe LIME is fine.
LIME's speed and simplicity could be perfect for that kind of quick diagnostic.
But if I'm, say, a bank needing to prove to regulators my loan model is fair,
Then SHAP's theoretical guarantees its consistency and its ability to provide both local and global views become indispensable. You need that robust, defensible explanation.
so the purpose internal debugging versus external auditing or compliance really dictates the tool. Makes sense. And you mentioned there's a comparison in the source materials.
Yes, we've included a breakdown comparing their strengths and weaknesses side by side, which should be helpful. And if we connect this toolkit back to the real world, the true test of explainable AI really comes in these high-stakes domains, places where a wrong or biased decision from an algorithm can have serious, maybe even irreversible consequences. We're talking about people's lives, their finances, public safety.
Yeah, the impact is huge.
In these areas, XAI isn't just a nice-to-have technical feature. It's becoming absolutely essential for managing risk, ensuring regulatory compliance, and, frankly, earning the social trust needed to even deploy these systems. Across healthcare, finance, autonomous systems, you see XAI acting as this crucial bridge, translating complex, opaque outputs into actions that are understandable and accountable.
Let's start with healthcare. The stakes couldn't be higher, right? AI has huge potential, but also huge risks if it's not transparent.
Exactly. The goal is to harness AI's power like in diagnostics while managing those risks. XAI helps turn AI from a black box giving answers into a transparent, collaborative partner for doctors.
Where are we seeing the biggest impact so far?
Clinical decision support is a major area, especially in medical imaging. There was a landmark study from Stanford on detecting pulmonary edema fluid in the lungs from chest x-rays.
Okay.
A standard AI was accurate but couldn't say why. The researchers used XAI, techniques like LIME, to generate heat maps right on the x-ray image. These heat maps highlighted the exact areas the AI thought showed edema.
Ah, so the doctors could actually see the AI's reasoning.
Precisely. They could visually verify it against their own expertise. This led to incredible precision, nearly 95%. But just as importantly, it massively increased physician trust and reduced uncertainty.
That's a powerful example. Are there others?
Definitely. Similar visual explanations are used for classifying skin cancer from images, helping dermatologists trust the findings. Beyond images, XAI is applied to complex models analyzing genomic data, predicting risk for diseases like Parkinson's, or guiding personalized cancer treatments by explaining why a certain therapy might work best for that patient's genetic makeup.
So in all these cases, the why helps the doctor make a better, more informed final decision.
Exactly. The AI offers insight, the explanation provides understanding, but the human retains control and responsibility. But using AI in medicine also brings up a lot of complex ethical and legal issues. XAI is key to navigating these. A huge concern is algorithmic bias. If AI learns from biased historical data,
It can perpetuate those biases,
yeah.
like associating outcomes with race or gender unfairly.
Yes, even if unintentionally through proxies, this can worsen health disparities. XAI tools are essential for auditing models, finding these biases, and correcting them.
What about when things go wrong? Liability.
That's incredibly tricky. If an AI-assisted diagnosis leads to harm, who's at fault? The developer, the hospital, the doctor, the IT team?
A black box makes that almost impossible to untangle.
Right. Surveys even show the public blames doctors, while doctors tend to blame the AI vendors. There's a disconnect. XAI helps by creating that transparent audit trail. The explanation, the heat map, the contributing factors becomes evidence of what the AI provided and why. That's crucial for fairly figuring out what happened.
And it impacts patient trust too, presumably.
Absolutely. Patients have a right to understand their care. XAI helps communicate the AI's role and reasoning, fostering that essential trust.
So the value of XAI in healthcare isn't just technical. It's about managing risk, both knowledge risk and legal risk.
That's a great way to put it. A doctor needs to know if an AI recommendation is justifiably accurate, if it meets the standard of care.
A black box just gives an answer, an assertion.
Whereas an XAI system turns that prediction into transparent evidence, the heat map, the key symptoms, the feature scores.
Which empowers the doctor.
It empowers them to critically evaluate it, integrate it with their own judgment, and build a defensible rationale for their decision. It makes the AI's output legally and professionally actionable. Now, shifting to finance. This is another area where XAI is booming. You've got high transaction volumes, complex risk, and heavy regulation.
And executives are worried about the lack of explainability.
It's a top concern, second only to regulation itself, according to surveys, and for good reason. Regulations globally are demanding transparency. In the U.S., the Equal Credit Opportunity Act, ECOA, requires specific reasons if you deny someone credit.
You can't just say no.
No. And the EU AI Act classifies financial AI as high risk, imposing strict transparency and explainability rules with hefty fines for noncompliance.
So the pressure is definitely on. Where are the main applications?
Credit scoring and lending is a huge one. Traditionally, getting denied a loan was frustratingly opaque. Now, XAI lets banks provide personalized reason codes, like denied due to high debt-to-income ratio or low score based on payment history.
Which meets compliance and helps the customer understand.
Exactly. It massively improves customer experience. There's a real-world example. Equifax's NeuroDecision uses XAI for this. Banks using it reported a 30% jump in customer satisfaction and a 25% drop in default prediction errors. Real business benefits.
Wow, that's significant. What about fraud?
AI is great at spotting weird patterns that might signal fraud, but sometimes flags legitimate transactions, false positives. XAI explains why a transaction was flagged may be an unusual location, a large purchase, a deviation from normal spending. This helps human analysts investigate efficiently, reduces friction for customers, and keeps security tight. And beyond these specific uses, XAI is helping tackle deeper systemic risks too, like unintentional discrimination. We talked about models using proxies like zip codes for race. XAI helps audit for and remove these biased links.
Preventing discriminatory lending practices.
Yes. And there's also the risk of hurting behavior in algorithmic trading. If many firms use similar complex opaque models, they might all react the same way to market signals.
Amplifying volatility and potentially causing crashes.
Potentially. Explainability can help supervisors understand these interdependencies before a crisis hits. You know, the role of XAI in finance is really evolving. It started as a defensive measure, a compliance shield.
Justifying decisions to avoid fines.
Right. But now it's seen as a proactive business enabler. Explaining a loan denial constructively can preserve the customer relationship, and the confidence XAI provides allows lenders to use alternative data like mobile payments, rent history, to assess thin-file customers.
People without much traditional credit history.
Exactly. This promotes financial inclusion and opens up new markets. So XAI becomes a competitive advantage, not just a cost.
Okay, let's move to perhaps the ultimate test. Autonomous systems, especially self-driving cars, AVs. Explainability seems absolutely fundamental here.
It really is. It's foundational for safety, validation, regulation, and just getting people to accept them. Public trust is still a major hurdle.
Understandably so.
XAI is seen as critical to bridging that trust gap, making AVs understandable and predictable.
Safety has to be number one. How does XAI help ensure that?
In several ways. One is real-time decision explanation for passengers. Systems are being developed to show or tell passengers why the car is doing something braking, changing lanes. Maybe a dashboard visual or a voice prompt like braking for pedestrian ahead.
To demystify the car's thinking and reduce anxiety.
Exactly. Then there's explaining perception and planning. XAI helps clarify how the AV identifies objects, predicts what others will do, and plans its own path. Some research uses interpretable models just for understanding other vehicles' intentions, making predictions more transparent.
And for debugging or accidents.
Intelligible logs from XAI systems are invaluable. Engineers use them to debug, regulators for certification, and if there is an accident, these logs provide an objective record to determine fault. But this raises a really interesting challenge for AVs. XAI needs to serve different audiences with different needs.
Right. The passenger needs something simple and instant.
Like obstacle detected. Very concise.
But the engineer or accident investigator needs immense detail.
They need granular logs, sensor data, model probabilities, internal states, the full picture to understand precisely why that decision was made.
So one explanation size doesn't fit all.
Not at all. A successful XAI system for AVs needs to be multi-layered, generating different explanations for different users. And the huge challenge is ensuring consistency and faithfulness across those layers. The simple explanation for the passenger must accurately reflect the complex reality in the engineering logs. Managing that is a key frontier.
You can really see how these applications fit into that broader risk framework we mentioned. We'll link to that summary for you. Okay, so we've seen the power and potential of XAI. But now let's get into some critical perspectives, because it's not a perfect solution, is it? There are limitations.
Absolutely. It's crucial to have a clear-eyed view. XAI isn't a magic bullet, and the pursuit of explainability itself has challenges and ongoing debates.
The biggest one seems to be that accuracy versus interpretability trade-off we touched on earlier.
It's fundamental. Generally, the models with the highest performance, deep neural nets, complex ensembles, are the least interpretable, the most opaque.
And the transparent ones, simple decision trees, linear models, often aren't powerful enough for complex problems, leading to lower accuracy.
Right. And while post-hoc methods like LIME and SHAP try to bridge this, they are approximations. They simplify the black box.
So their explanations aren't guaranteed to be perfectly faithful to what's really going on inside.
Exactly. Some critics even argue they are necessarily wrong because they have to simplify an often inscrutable process. It forces a tough choice. Prioritize raw power or human understanding. And closely related is the subjectivity of a good explanation. What does good even mean here?
It depends on who's asking, right?
Entirely. There's no universal standard. What's useful depends on the context, the person's knowledge, their goals. A list of SHAP values might be great for a data scientist, but meaningless to a patient.
So explanation goodness needs to be tested with actual users.
It absolutely does. We need user-centric evaluation to see if an explanation actually helps someone understand and act effectively. But honestly, that kind of rigorous human testing is still pretty rare in XAI research.
Okay, and that leads to maybe the most worrying part, the dangers of misleading or harmful explanations.
Yes, this is critical. XAI isn't neutral. Applied badly, it can cause problems. First, that lack of fidelity we mentioned. The post-hoc explanation might just not accurately reflect the model's true reasoning.
Second,
The risk of creating false confidence and over-reliance. A plausible-sounding explanation, even if incomplete or wrong, might make users trust a flawed AI too much.
studies show people tend to overtrust AI advice anyway.
They often do, and just providing an explanation doesn't always fix that, especially if the explanation itself isn't carefully designed and validated.
And third, the risk of manipulation. You called it fair washing.
Right. Since explanations are often generated separately, someone could theoretically design an explanation system to hide bias. It could highlight innocent factors while concealing that the model is actually using problematic variables, tricking users or regulators, a very serious concern.
Given those risks, especially with post-hoc methods, it raises that question again. Should we just avoid explaining black boxes for high-stakes stuff? Should we insist on using only intrinsically interpretable models?
There's a prominent school of thought arguing exactly that, yes. Even if it means accepting potentially lower accuracy.
It's a philosophical debate almost about how humans and AI should collaborate.
It really is. The post-hoc approach tries to translate potentially alien AI reasoning for us. The intrinsic approach demands AI conforms to human understandable structures from the start.
And the choice has big implications for innovation, risk, ethics.
Huge implications. And connecting this to the bigger picture, XAI is operating within this rapidly evolving ethical and regulatory landscape. That context dictates what counts as a sufficient explanation.
You mentioned fate earlier. Fairness, accountability, transparency, ethics. How does XAI fit in?
XAI is the key enabler. Transparency is achieved through XAI tools. Accountability is impossible without that transparency. Fairness requires transparency via XAI for auditing and mitigation. And ethics is the overarching framework guiding why we need all of this.
And regulations are starting to mandate this. You mentioned the EU versus US approaches.
Yes, the EU AI Act is taking a comprehensive risk-based approach. High-risk AI in finance, healthcare, employment, etc., faces strict rules on accuracy, oversight, and explicitly transparency and explainability. It creates that right to explanation with big potential fines.
Whereas the US is more fragmented, sector by sector.
Currently, yes, a patchwork quilt of existing laws like ECOA for credit, agency actions like the FDA for medical AI, and state-level rules. It's less uniform.
But the overall direction globally is towards demanding more transparency.
Undeniably. Even with different approaches, the principles of transparency, fairness, accountability are becoming prerequisites for trustworthy AI. The divergence means companies operating globally need flexible XAI strategies to meet varied requirements, often aiming for the highest standard.
So looking ahead, where does XAI go from here? Demand for transparency isn't fading.
Not at all, it's intensifying. XAI is moving from a niche field to a cornerstone of responsible tech.
What are the key technical trends driving this?
One big shift is towards interactive and personalized explanations, moving beyond static reports to dynamic interfaces. Users will be able to probe reasoning, ask what-if questions, get explanations tailored to them. It turns explanation into a dialogue.
That sounds much more useful.
Another exciting area is neurosymbolic AI, hybridizing deep learning's pattern recognition with symbolic AI's logical reasoning. The hope is to create models that are both high performance and intrinsically more interpretable, potentially easing that accuracy interpretability trade-off.
Making models simpler is also a goal.
Yes. Through techniques like model distillation, a complex teacher model trains a simpler, interpretable student model to mimic it, or pruning neural networks, removing redundant parts to simplify them without losing too much performance.
And integrating XAI into the development process itself. MLOps.
Crucial, integrating XAI tools into machine learning operations, MLOps, pipelines, allows for continuous monitoring of deployed models for bias, fairness drifts, performance issues throughout their life cycle. It makes accountability continuous, not just a one-off check. And these technical trends are happening as the regulatory landscape hardens. We're moving from voluntary principles to mandatory legal requirements for AI transparency. It's becoming a necessity. It's all part of this bigger push towards human-centric AI systems designed to be trustworthy, aligned with our values, serving our well-being. XAI is critical for that vision.
So what are the takeaways, strategic recommendations?
For technology leaders, adopt a risk-based approach like the EU AI Act. Use rigorous XAI for high-risk systems. Maintain a diverse toolkit, intrinsic models where possible, post-hoc where needed. And please prioritize user-centric evaluation to ensure explanations actually work for people.
For policymakers, strive for international harmonization to reduce compliance chaos. Fund interdisciplinary research, this isn't just a tech problem, and promote public, diverse data sets to combat bias at the source.
And for researchers, tackle that explanation goodness problem, develop objective metrics, improve the fidelity of post-hoc methods, quantify their uncertainty, and study the cognitive effects of explanations, how they really impact human trust and decision-making.
Okay, so wrapping up this deep dive, we've explored why XAI is so vital, digging into the black box problem and its risks. We've looked at the tools like LIME and SH used to gain understanding. We saw XAI in action in critical fields like healthcare, finance, and autonomous vehicles, building trust, enabling accountability. And we considered the challenges, the debates, and the future directions. It really feels like explainable AI isn't just about making machines smarter, but about making them more compatible with us, more understandable.
And that leaves us with a really crucial question to think about, doesn't it? As AI keeps getting more powerful, how do we make sure we don't end up in a future run by decisions we just can't comprehend, let alone challenge? It really isn't just about building smarter machines. It's about building machines we can genuinely understand and truly trust.
A really profound thought to leave you all with. We hope this deep dive has given you a clearer view of the world of explainable AI. Until next time, keep exploring, keep questioning, and keep learning.